Hello, everyone. Thank you so much for joining. My name is Mohammed Shahbaz, and today I'm really excited to present my dissertation, From Failure to Fidelity, Enabling Scalable Sim-to-Real LiDAR Perception through Realistic Digital Twins. Before diving deeper into the technical details, I would like to take a moment to express my gratitude to people who made this journey possible. Since I'm very thankful, sincerely thankful, grateful to Dr. Shari Agarwal for his, insightful guidance and empowering me to thrive in my own way. I sincerely thank Dr. Karan Sikka for his early mentorship that laid the foundation of this research. Um, and of course, I extend my thanks to the esteemed committee members, Dr. Samuel Hassan and Dr. Shepaz, for their valuable time and mentorship. I'm also really grateful to the people and mentors in my academic journey, especially Dr. Kashif Sattar, Dr. Bilal Bashir, Dr. Noreen Zafar, Dr. Asifullah Khan, and Dr. Faz Minhas. Their guidance played a really formative role in shaping who I am today. Thank you so much, everyone. And let's jump in. So let me briefly highlight the key contributions that emerged from this dissertation. So there are 5 journal publications at various stages from submission to publication. There is a conference with proceedings and some general presentations. I also have released UrbanTwin dataset on Harvard Dataverse, which consists of multiple roadside LiDAR datasets. To help you follow along, let me briefly walk you through presentation's roadmap. We'll start with the introduction, where I will discuss the motivations, the guiding questions, and the research plan behind this work. And from there, we will go to the theme from failure. Here, actually, we will look at the research that was not scalable, but had a lot of lessons that laid the foundation for the later work to fidelity part. And this is actually the fidelity to fidelity part is the part where the core or the main research lies. Here we developed high fidelity digital twins and constructed real in domain, or you can say very realistic roadside LiDAR sets that can be used for real LiDAR perception in the real world. And towards the end, I will also present the software contribution, which is LiGuard. It is a published research, so it is available on the GitHub as well. For the people to rapidly and interactively do the LiDAR research. It's a very useful tool. We will talk about this. And then the conclusion, where we will summarize the research, some of the limitations of this work, and how we are thinking about the future of this work. And then you may ask questions. Let's start with the problem. Transportation systems across the world face serious challenges from traffic congestion and accidents. In fact, US loses $500 billion annually for traffic congestion and accidents, and this amount is like 6 times globally. Intelligent transportation systems, or ITS, have emerged as a promising approach to address these challenges. As ITS brings together advanced sensing, analytics, and decision making, like all together. But the core of this is, of course, sensing. The first part where you perceive the traffic is very important. And this is where my research lies in. Okay, so you see, historically, we had these sensors like loop detectors and cameras. Cameras are much more recent, of course. Loop detectors can only detect like in terms of counting, so they are not spatially aware, so there is no localization. They just count the objects. Cameras are much more robust in the sense that they can detect and track vehicles. However, there is no active depth perception, which means that they do not know how far an object is accurately. And they are prone to lightning and weather conditions. So at night, they don't work. And therefore, my research focuses on this like more recent, more robust sensors called LiDAR sensors. LiDAR, or light detection and ranging, is a technology where the sensor actually scans the environment using LiDAR pulses, so it is like an active sensor. And it is not prone to like lightning or weather conditions. It works at day and night the same, in the fog the same, in the rain the same. Um, and I have a few examples here just to showcase. You see, like camera and LiDAR, when they are compared in the same settings of fog, rain, and light, you see that the cameras fail actually, and the LiDAR-based vehicles they tackle the situation very effectively because the LiDAR sensor is actually more robust. So we can say that the LiDAR is much more complementing sensor for the ITS, along with the camera, definitely. So, however, when we talk about LiDAR perception, it is just like any other computer vision problem. It is primarily solved using deep neural networks. And deep neural networks, to train them, they require labeled data. And the problem in the LiDAR domain is that it has very limited data, especially for the roadside LiDAR datasets. And the reason behind that is that LiDAR datasets are very hard to make because of the effort, time, and financial cost that is needed. So for example, in the image domain, the drawing bounding boxes is much easier because it's just a rectangle. But in the LiDAR space, which is also sparse, very hard to see, you have to draw these 3D bounding boxes. So it requires much more effort, and that translates to time and the financial cost. So for example, Lumpy dataset, which is a LiDAR dataset of a single intersection in Germany, they required 550 hours plus time to just record and label the data set for this one intersection. And according to this Amazon SageMaker quote, you can see like 10,000 frames of LiDAR. You would require roughly $16,000 to label that data. So it is actually really hard to make these data sets. So based on that, these challenges kind of motivate me to define the four core research questions, like how we can make the data sets or like make the systems which are much more efficient and costless in creating the LiDAR perception. So the first question that we ask is that in the AV domain, there are multiple LiDAR data sets and models. So can we transfer those models to the roadside LiDAR? The second question is that can we use self-supervision to kind of like perceive in the LiDAR domain? So again, it doesn't require humans to label the data. Can we use simulation to like create models that can be applied to the real world? And the last question is like, it is more general, yet it is an important question that we ask because LiDAR data is complex to work on. So can we develop a software that can streamline LiDAR research? And we aim to open source it. Now, putting all those questions together, the goal becomes this: enable scalable LiDAR perception for ITS, minimizing cost, time, and effort through modeling digital twins and sim to real learning. And to achieve this goal, we have multiple objectives. So the first objective is like very direct. So if we want to study if the AV LiDAR algorithms and models can be transferred to roadside LiDAR, we analyze empirically if data in the models in the AV domain can be used for LiDAR perception. Second is also very direct, self-supervision. So we explore if self-supervision can help train these deep object detectors for scalable LiDAR-based perception. Simulation, however, had more objectives because this is like kind of the area where you have to like study more, you have to think about more. So there are four different objectives. So we first look into a method where we create a simulation that is much more realistic and then generate data from that simulation. And then using that data, we train the model and evaluate them in the real world. And then we interrogate those models that why they work or they don't work. And for the software development, we have this objective that we develop LiDAR research, facilitate the LiDAR research through this open source software framework. All right, so combining all these objectives into a research plan. So what this research plan basically says is that research question 1 to 3 is more like in series. So we do objective 1, objective 2, and 3, 4, 5, 6, all of them like in series. Now, however, the objective 7, which is developing software, we do it along the way. Um, because we were also doing the research kind of like on our own, and we were using this software and we were developing this. So this is like more like a parallel objective that we have achieved. Um, so now let's begin with the first theme from failure part, where we tried to develop algorithms to directly transfer AV LiDAR algorithms towards the roadside LiDAR. The objective is analyze empirically if data and models in AV domain can be used for roadside LiDAR perception. The first thing that we test is 2D to 3D transfer. This is basically a model that takes input 2D image and gives us 3D bounding boxes. And this model is trained on Kitty dataset. Now, why we use this is because 2D is much more solved problem. So, it should be much more general, should be much more generalizable. But when we try this model on our roadside LiDAR data set, we see that it fails. It fails miserably, approximately 0, MAP score, which basically tells that, okay, how good your detections are. So this fails. And there are numerous hallucination means that it is giving objects where there are no objects. So we say naive or direct transfer across modalities fail because we are changing the modality from camera to LiDAR. So naive or direct transfer of these modalities fail. The second experiment series is the 3D to 3D experiment, which is basically LiDAR models which take input point cloud and give you the labels, the detections. We transfer those models from the AV domain to the roadside LiDAR. So this model, which is basically point pillars trained on the Kitty dataset, when we test it on the intersection LiDAR dataset, it fails again. And we conduct this experiment multiple times using different models, with the second or with Pixar. And everywhere we see the same, that, it works very well on the data that it is trained on the vehicle dataset. However, it doesn't work on the roadside LiDAR. So we also say that naive or direct transfer across domain also fails. And just, looking at why this fails is actually a very established term in deep learning, and it's called a domain shift problem. You see, like a LiDAR that is on top of a vehicle, it sees the data distribution or the point distribution of the point cloud or the LiDAR data that it is capturing from a very different perspective. So you see the point cloud here has more points on the sides of the cars rather than on the top. But when you move this LiDAR, above the road, connect it with the pole and make it a roadside LiDAR, now the point distribution changes and more points are actually from the top of the vehicle. So this distribution shift actually makes the models that are trained in the AV domain fail in the roadside LiDAR domain. So what we come up with is that, okay, let's train the model in using the data sets that are captured for roadside LiDAR perception. And we train 7 SOTA models. And what we see is that this works, right? So here you see the scores are there. They are not 0 scores. They are not very good scores, but they are still, the scores are there. So we see that this works, which means that the AV models that were developed for autonomous vehicles domain, those models are transferable. So if you retrain them, they work. So model themselves are not domain dependent. The data is, okay. So this kind of make us focus on, okay, let's create the data or like make the way to label the roadside LiDAR data. So that's where our second objective comes in. Explore self-supervision to train deep object detectors for scalable LiDAR perception. And we do some like literature review and research gap, and the summary of it is that roadside LiDAR lacked labeled data. Self-supervision using background filtering and clustering exist. Deep learning can leverage such self-supervision. However, the gap is that this self-supervision has been used to kind of train the models very in a very simple way. So what we found is that teacher-student modeling, which I will just explain in a bit, is not there. What is teacher-student modeling? So in the teacher-student modeling, we have a teacher model, which is not a deep learning model. It is like an algorithmic model with a heuristical kind of approach. Um, and what we do is like we take the unlabeled point cloud and we pre-process it, so crop it to the region of interest, then apply background filtering, do clustering, and then this clustering and kind of like regress the bounding box on top of this, and this gives us like unsupervised labels, and we use those labels to train the student model, which should work effectively. Now, this technique is not new. However, this teacher model is like it's prone to like because it gives noisy label, it doesn't give very good labels. So we had to develop some good things, which are like, okay, background filter. We developed our own background algorithm, which is background filtering algorithm, which was robust. And we use the common clustering DB-scan algorithm. And what we see is that if we use single a teacher, that gives us some scores. It is still, you see this like top line here. Uh, but what the novelty is that if we use multiple teachers and we collect the data from multiple locations, um, and then combine those noisy labels from multiple locations and then train the student model on top of that, it really works. And we see like a more than 50% MEP increase here. However, there is a problem because for this sort of experiment to work, you would need data that is similar. So for example, if you have a roadside LiDAR data from one location and from other location, those two locations should have like similarity. So for example, in this case, we use two data sets, the UCF intersection LiDAR and the Australian State University APLS data set. Both of these two data sets are like captured from a university environment. So there is like same sort of like pedestrian and vehicular activity. And the LiDARs are both at the same height and pose as well. So that's why like it works. However, there is no more such data available. So this technique is not like scalable. So we check that, okay, if we, train the student on its own labels, maybe it will improve. And we do that for like, multiple iterations. And we see after 3 iterations, and, the model is like kind of not improving. So it's like detection score is like jumping back and forth. So basically it saturates. Um, so this actually takes us to the part where we say, okay, since this sort of like similar data will not be available, let's use the simulation for that. And the key goal here is to make the simulations high fidelity. So that's why we say it to fidelity. Here we have multiple objectives. The first objective is to create a very highly realistic or like high fidelity digital twin of a location and then do the simulation in that location virtually and then get the data. Um, and of course, this is the literature review, and the main gap is like building digital twins is a very resource heavy task. So how do we like make this much more efficient? So we come up with this 5-stage plan where we get the data about a location first. We can gather everything about that. Okay, so what are the speed limits? What is the road network there? What are the types of the vehicles? What is their distribution there? And then use that data to kind of construct the geometric scene, like a 3D model of that location. And then in that location, we make it like a simulation ready environment and then use the very like commonly used simulator known as Carla, and simulate the traffic and sensors in that to generate this high quality data. So we would go through them one by one. So the first part is site context and data acquisition. Here, we gathered the data such as road layouts, speed limits, lane configurations, traffic signals, surrounding structures, and you can see we can get it from various resources like Google Maps, Google Street View, or like road topology data from OpenStreetMaps. And even if we have video footage to kind of tell how much traffic is there, how it looks. This is basically the part where you gather the data and assets. And then the second part is you have this 3D model of the location that you were gathering. So these 3D structures that you captured. Now you pre-process them and you kind of make them into the region of interest. So this is actually the lumpy dataset, the real lumpy dataset's location. So we just get a 3D model of that location and we crop it to the region of interest. And then we use different tools like to get this 3D data, we use cesium, and then to add it or make cropping and converting it to like region of interest, we use Blender. Blender is an open source tool, so it's like free to use. Here in the second part, like after pre-processing, what we do is like we find out where the lidars are going to be in this virtual world, and we have to match them according to the real world. So in the real world, where the lidars are or where they are going to be, in the case like if you are working for a location where there are no lidars so far, but in the plan you would know that okay, where the lidars are going to be placed. Uh, so we kind of like pinpoint those locations. And then we import this whole 3D model into the Roadrunner. So Roadrunner is a MATLAB's tool which can be used to like create these roads and speed limits and intersections and everything. So you import it to the Roadrunner and use the tools like OpenStreetMaps and Open Topography to know what are the elevations of the road, what are the how the intersection is, like how the turns take place at an intersection, what is the signal timing, what are the speed limits, all those things you can set those here. And then you kind of make everything into a loop so that you like the traffic that is generated in this virtual environment kind of like stays the same distribution wise. And then you export it into like a Carla film box format, which is the standard format that can be used in the Carla simulator. So in the Carla, you import the map, and there are various settings that you do. So for example, you check all the trajectories of the vehicles are good, intersection is good. You also check how many spawn points you have. So for example, if you have 100 spawn points and usually you have more than 100 vehicles, so you would like to increase the spawn points. That is very easy. You just copy paste and place new spawn points. And that is basically our digital twin. Now you see like this digital twin is much more realistic in the sense that it is um, it captures the 3D geometry of the real world. Okay. It has exact road replicas. So it captures the roads that are exactly matching the real world. The speed limits even, the signal timing. So this digital twin is a virtual environment which kind of resembles the real world very closely. Okay. So the next part is we deploy the virtual LiDARs at the locations that we found earlier in the first stage, and then we simulate the traffic in that. Um, and then this is a simulation, so you just start recording the LiDAR virtual sensors data. And what you see is that the LiDAR data that is generated versus the real LiDAR data is very similar. Okay. And since it is simulation, you can generate all sorts of labels. Okay. So you have already know where the objects are. So object detection labels, tracking labels, segmentation labels of both kind, like semantic and instance segmentation. So we have made the method to kind of create how to create these highly realistic LiDAR datasets. So the next objective is naturally, okay, let's generate an in-domain synthetic LiDAR datasets against real datasets. So we went ahead, and this is the literature review and research gaps, where the gap basically is that synthetic datasets that replicate real world realistically do not exist. So there are synthetic datasets, but those datasets do not capture any real world information. So they are just captured from these imaginary virtual towns. So, to fill this gap, what we do is we generate the three LiDAR datasets, roadside LiDAR datasets for three real world datasets. Okay, so lumpy, v2x real IC, plum graph intersection dataset, all of these datasets are like very well established real datasets in the roadside LiDAR domain. We create the replicas for three of them, and we just prefix them with UT mean urban twin datasets, which is like the digital twin. The name is coming from there. So these are the synthetic datasets that we develop. And we generated so far like 10,000 frames for each of these datasets, but this is simulation, right? So you can generate like 100,000, however much data you need, you can generate that. So we generate 10,000 and we generate the 6 classes, and we support all the object detection, object tracking, semantic and segmentation categories. So all the spectrum of LiDAR perception, we generate the data for that. And this is just a data description, you can say, or like statistically and distributional comparison to real data sets. So here in the like greenish is the real data set, and the orange ones are the data set numbers, which are from these digital twin synthesized or like these synthetic data sets that we generate. And what you see is that like because this is like a same kind of 3D environment, same kind of LiDAR sensors virtually installed. So the number of like the number of points per frame are same. The scene complexity in terms of number of objects per frame is same. The class distribution even is same. So it's basically, because you created the simulation after a real world location, the data that is captured from the simulation versus the real data kind of matches very closely to each other. In the normalized means, you can actually see that the overlap is kind of very high. And this kind of tells that this data is statistically and distributionally is very similar to real data. But we do not stop here. So what we say is that, okay, this data set looks very real. Let's train the models on this and check if they can compare to the models that are trained on real data. And that's what we see is that we train the second model on a complete, like purely simulation data. And we see that it works very well. It works like it beats almost all the models except this one, attention fuse model, which actually uses the fusion for LiDAR and camera, both sorts of data to predict this eye. And we are kind of like very close to that. So which means that these data sets are not just like statistically same when you train the models on top of them, they actually work on the real data as well. So this data set was trained on simulation data, but was tested on actual real data. So the implications of this research is that now you can generate low cost in domain data. You can generate even hazardous or rare events that are not available in the real world to kind of make the data sets much more robust, to train much more robust models. And there is no biasness in labels. So any model, any label that you generate is like kind of perfect. So this takes us to the next objective, which is, we generated this synthetic data, but let's, do some more evaluation and see if this synthetic data set can be used in the real world, like with another data set. So we generated 3 data sets. So we go with the second data set, and this is just the literature review on the research gap. And the research gap basically here is that the simulations, so naive sim to real learning performs poorly. Okay, so we are going to actually the sim to real learning part, because in the last we trained the models, but we did not actually like went for a very accurate or like very in-depth, you can say, like comparison of real versus the synthetic LiDAR data. This is the part where we explore the sim to real learning. Okay, so the research kind of tells that, okay, naive sim to real learning is done previously and it performs very poorly. Sensor modeling and domain adaptations were also explored previously. And although simulator models have improved sensors, the 3D assets still lack fidelity, which means that, the data sets that are generated are not very real. And any solutions to simulations are mostly post hoc, which means that the simulation data is generated and then there is some processing done on top of the data or the model to kind of like fill the deficiencies of the fidelity that is not present. So that is the gap that we want to fill, that we use our data sets and we train the models without changing any configuration, so of the models, and train just them like with the very basic settings, and we see if that work. And this is kind of like a mathematical problem formulation. So what the essence of this is that the real data, which is d real, is drawn from like a distribution that is p real, and we have a simulated data that is drawn from p sim, which is simulated simulation data distribution. And our goal is to kind of make this divergence between the p sim and p real approach zero. And this is the hypothesis is that the data generated using those high fidelity digital twins that we just developed, this should work. Okay. Um, so we test very like deeply how everything works. So we take the model. The model is called seed. It is trained on synthetic data, the data that we just developed with using high fidelity digital twins, but the second data set. So the first data set we tested in the previous one. So here we are diving more deeper and for another data set, lumpy, UT lumpy. Okay. So, and then we train seed2 model on real data. So first we train on the synthetic data and then on the real data. And then we compare multiple things. The first thing that we compare is that during training, these two models that were trained on real and data and the synthetic data, how their loss trend is, coming. So we see that the loss trend actually matches very nicely, which kind of tells that the models are training on both data sets kind of the same, which is a good thing because this kind of tells that, okay, both the models are actually seeing kind of the same data. And then we test, okay, what is their accuracy? So what we see, surprisingly, is that the model that is trained on synthetic data performs on real data better than the model who is trained on the real data, which is very strange because the real data is actually real from the real location and was labeled by humans. However, what we feel is that this is because of the human biasness. So some of like human labels are not perfect, so model is not very good at generalization on all those. And since our like synthetic data set has these perfect labels, so that's why it has slightly more score given the same settings. So this surprise that we got, we had this thing that, okay, this, it means that it is working very nicely. However, we wanted to interrogate more. Like we wanted to check internal representations of the models and see like if those matches as well. And here you see t-SNE and UMAP plots. What t-SNE and UMAP does is that they take the like very high dimensional features into 2 or 3 dimensional features, and you can plot them to kind of see how those features are there, like how those features look like. And this is more like a qualitative analysis. And we do that analysis on the latent features. What latent features are is that a model, the seed model has multiple layers. So we just use the backbone of that model and we extract the features from the backbone. And then we use these t-SNE and UMAP techniques to kind of make them lower dimensional into 2D space, and we plot them. And what we see is that when we plot the distribution, the t-SNE plot of the realistic data set and the target real data set, they match very nicely, very closely in both of the cases. But when we compare them with other data sets, they do not overlap. So the green is overlap and the red is not overlap. So you can see very clearly that the synthetic data sets that we generate for a target location match the target location very realistically, that the model's internal representations even are like matching very nicely. But this is a qualitative analysis. So what we do is like we go for more quantitative analysis and we check 4 different matrices. So the camphor distance is we test it for the real point cloud data and the synthetic point cloud data. And the camphor distance is more like Euclidean distance between point clouds. So The distance is actually very low for synthetic versus the target real data set. And for other data sets, it's more. So it kind of tells that, these data sets are like geometrically also very close. Camphor distance tells that. And then when we compare the latent features, which are the features from the backbone of a neural network, and we use a techniques such as maximum mean discrepancy, earth movers distance, and pressure distance. All these matrices are basically, just the distance matrices between two sets of points. And what we see is that synthetic versus target real always is lowest, almost zero in some cases. Earth mover distance has some value, but compared to the other ones, it is much more lower. So in conclusion, we can say that these data sets that we made are very closely matching to real data sets. So that's why when we train the models on them, they are practical in the real world. So this solves a big challenge. Okay, so let's move towards the ending of this, and let me introduce to the software contribution. LiGuard is actually very big software that is very useful. So the objective for this development was facilitate LiDAR research because LiDAR data is very hard to work on. So we developed this LiGuard software. So LiGuard is an open source framework for rapid and interactive LiDAR research. We did some literature review, and we found that there are other libraries and there are other softwares out there. However, they have different limitations. So for example, some of them just only process single point cloud at a time, and they are not good for sequential point cloud data that is coming from these LiDAR sensors in the ITS. They have C++ core, which is like very hard to kind of master. So it's very hard to like kind of change them. And they have incomplete Python bindings or incomplete Python support. Most of the libraries, if you talk about Python, were developed for the developer, like were focused for developers and not like researchers who want to like get the results rather than going into the intricacies of software development. Um, some of them are good, but like some of the libraries are good and they have a CLI based interface, but CLI is very hard to work on again. So it's like a command line interface where you just have to type everything. So what was the gap that we identified is that, Python based interactive GUI powered kind of like software is not there. So LiGuard focused all of that. And this is the GUI of the LiGuard. So you see on the left side, we have this highly adaptable configuration window, which is like you can modify it just by a few lines in your configuration, and you can add multiple algorithms very easily. And in the center, we have this very strong visualizer that can visualize point clouds, the bounding boxes, the trajectories, segmentation labels, or like clusters, everything in a point cloud domain. And then we have this logger window on the right, which kind of tells you if you implement your custom algorithms, it would quickly tell, okay, how the algorithms are being executed. If there is some error, it would show that error there. And this is the LiGuard's architecture, how it is developed. So I know this diagram feels very like, it has a lot of components to it, but in summary, what it supports is that it has this live data streaming, which means you can connect a LiDAR directly to it and kind of see what's going on. You can apply all the algorithms on the live data stream coming from the LiDAR. It has these structured project directories for easy sharing, which means that if you created some project in LiGuard, you can share it with other researchers very easily with just, sharing one folder. It contains all of the configurations and settings in that. It have these interactive configuration support, which means that you can enable or disable any algorithm interactively. You don't have to like go and change it in the code. It can use single and multi-modality data, which means that you can combine data from multiple LiDARs, from multiple cameras or LiDARs, and can kind of perform algorithms on top of that. It does everything as a multi-threaded operation, which means that if it is much more efficient in using your computer, and it has powerful visualization support, and it logs all the errors. Compared to other libraries, LiGuard has a lot of features, including the Python support, single, multi-frame, multiple frames, point cloud operations, image operations. It has interactive GUI and everything. And so it's like it covers a lot of spectrum, and it is in development. One version is actually published in the Journal of Open Source Software, so you can actually download it in a working condition. So but more updates are coming. Um, so it has these built-in algorithms in it. So many of the like common things like cropping a point cloud, rotating a point cloud, these sorts of algorithms or basic background filters, all of those are implemented. Uh, and just as a good thing to tell here is that all the visualizations that you have seen so far of the LiDAR data and the image data were all actually the screenshots from the LiGuard. So it is actually, we actually use it on a daily basis for our LiDAR research. So it's very useful. And there are many more kind of features, and more are coming because it's an open source. So everyone is welcome to use this or contribute towards this project. Um, so in summary, we have identified challenges in scalable LiDAR perception. We developed DinoStar, which was the self-supervised learning framework. We developed a method to create high fidelity digital twins. We created multiple data sets using those, that method that we created. We tested that method in sim to real learning and proved that it works. And we released LiGuard, which is an open source software toolkit for streamlining LiDAR research. So together, all of these contributions can be said as like a practical scalable blueprint for more generalizable LiDAR perception in intelligent transportation systems. Uh, However, like any research work, it also has limitations. So for example, pedestrian simulations lack fidelity at this time. So that's why we do not generate pedestrian datasets. We generate vehicular LiDAR datasets where you have the vehicles moving at an intersection and or like at any place, but not the pedestrians, because Carla simulator that we use in this methodology lacks very realistic pedestrians, but that will improve, or we can create our own assets. So that is one of the limitation. Modeling digital twin is like very easy now because we have like laid out a very good framework that anybody can use to create the digital twins. However, it is not fully automated, so it still needs some human involvement. So that is one of the limitations. Sim to real learning, we have tested it, at two different data sets. We have also we are going to test it for the real world settings. Um, However, so far we have only tested it for the data sets that are already there, and not for the scenarios where there is no LiDAR so far and the LiDAR is placing. So that's actually what we are working towards, and that brings us to the future directions. So the first thing that we aim to do is like improve the pedestrian simulations by creating realistic assets for pedestrians in our simulations, then adding more automation to creating the digital twin so that it's like more like a automated system rather than a human actually downloading the model and then cropping the model and all that. And then test we want to test our algorithms in the real world setting. So we want to test it in the work zone environment as well as the intersection environment, and we want to grow the LiGuard open source ecosystem. And just as some final notes is that we are not stopping. So the future directions that we said, we are already working on that. So for example, the roadside LiDAR data we have already collected using this rig that we designed. And this data set was captured from this UCF intersection. It is about 10 feet high above the ground, and it contains roughly 6 hours of point cloud plus camera data at this intersection. We are also moving towards work zone LiDAR perception, using our automatic methodology to kind of come up with applications for work zones. And for that, we are also working. So we have already LiDARs installed, and the data is going to start streaming soon. And we really hope that, this will be really practical, actual application that will be coming out of this research. So thank you so much. And if you have any questions, please tell. Thank you so much again.